kidneys are able to eliminate mostly water-soluble compounds. So one of the main functions, one of the main actions of biotransformation is exactly transforming lipophilic or heavily lipophilic compounds into more water-soluble compounds so that the kidneys can eliminate those compounds. Just like the liver is the organ mainly involved in biotransformation, the kidney is the main organ involved in elimination or excretion. However, elimination of gases or any volatile compound, of course, can happen, in fact happens mainly in the lungs, and also this is, let's say, a secondary route of elimination. The liver can eliminate some particular compounds through bile directly into the intestine. Okay. Of course, some small amount of compounds can be eliminated through other routes, just like nails, hair, skin, sweat, also milk. But all of these are, let's say, a small part or an important part just for some specific compounds, not generally. Okay, generally, of course, kidneys are the most important ones. Okay, so this is the last slide from yesterday. Just one moment, so this one. Okay. Let's see if, okay, it's already. Sorry, just a moment, because I need to change. Okay. No. Then is this one? Okay. Okay, sorry for the interruption. Okay, in biotransformation, I wanted to very briefly expand concepts on oxidation and reduction. We have already seen redox reactions. So we already know or remember that every time there's an oxidation, there's also a reduction of some other species. However, in the biological reactions and the biological effects we want to see in the following of the lessons, we often want to focus just on one part of the reaction, just on the reduction or just on the oxidation. So you will hear me often talk about this compound is oxidized to, this other compound is reduced to, and so on and so forth. Of course, you should always remember that if I say this compound is oxidized to, this means that something else is also reduced, okay? But probably it's not important in this moment to talk about it, so I will just focus on the oxidation part, and so on, okay? How can we know that a compound is oxidized or reduced? We can calculate oxidation numbers, okay? If we have ions that are just one atom, single atom ions, the oxidation number is exactly the charge on the ion. So Na plus is +1, S2 minus is -2, and so on and so forth. Okay, so oxidation numbers in single atoms is quite simple. If we have compounds, so for example, ions or non-ions, not ionic compounds, we have to calculate our oxidation numbers so that the sum of all oxidation numbers is equal to the charge, or to 0 if there's not a charge, of the total compound. So, for example, here we have NO3 minus, so we know that the sum of all oxidation numbers should be -1, okay? In almost all compounds except peroxides and oxygen molecules, oxygen has almost always oxidation number -2, except peroxides, where oxygen is -1, and the oxygen molecule, where oxygen, of course, is 0, because it is an homoatomic molecule, so the two atoms will have the same charge, which is 0. But everywhere oxygen is -2. So we have 3 oxygens, each of them has -2. So we have 3 times -2. This means -6. The total should be -1. So of course, nitrogen should be +5 in order to give -1. And the same calculation we can do for the sulfate atom, SO4 2-. In this case, we have 4 oxygens. Each of them is 2-. So 4 times -2 is -8. So, of course, sulfur must be +6 in order to produce the -2 total. In this case, we have to remember, okay, the oxidation numbers, the most frequent oxidation numbers. And we may remember that sodium is in the first period, in the first column of the periodic table. So it is an alkaline metal, and so it only can take the +1 charge. So if Na is +1, of course, Cl must be, chlorine in this case, must be -1. And in most compounds, except when it is bound to oxygen, chloride, if it is an ion, it will be a -1 ion, okay? So Na is +1, the total charge is 0, so chloride, of course, must be -1. Chlorine must be -1, so it is chloride ion, and the total is 0. I have already said that homoatomic molecules that don't have a charge, just like bromine or nitrogen or oxygen, O2, if the sum must be 0, those atoms will have, both bromide atoms will have the same electronegativity, so their oxidation number will be the same, and it should be, of course, exactly 0. And this is true for any homoatomic molecules that don't have a charge. I have already also recalled that alkali metals, group 1A, the first column, are always +1, while alkaline earth metals, group 2, called 2A, column 2, are always +2. Again, this is already known that oxygen is almost always -2, except in oxygen molecules, where it is 0, and in peroxide. Peroxide are this kind of compound where we have two residues, two usually organic residues, and the oxygen-oxygen bond. These are peroxides, and here oxygen has -1 oxidation number. Hydrogen, you may remember that hydrogen is the first element in the first column, so its electronegativity is quite low. So hydrogen is almost always +1, with exception, of course, again, of the homoatomic hydrogen molecule, where, of course, it is 0, and when it is bound to some metals, in particular, of course, alkaline metals, because alkaline metals always have +1. So if Na is +1, of course, hydrogen here must be -1 since the molecule is neutral, doesn't have a charge. Fluorine is the most electronegative atom. So, of course, it cannot be, let's say, anything else than -1. It is in the 7th column, 7th group, so it has 7 electrons in the valence level, and in order to have the complete level, it can take 1 electron, so -1, and mostly it doesn't do anything else. Okay, so it's always -1. The other halogens, as we have seen in sodium chloride, so in metals and in compounds with metals and with hydrogen, the oxidation number is always -2. And Ai, in this case, sodium iodide, sodium is +1, so iodine is -1. Aluminium chloride, AlCl3. Aluminium, when it is bound to some electronegative compound like halogens, is +3. This is the 3rd column, so +3. And of course, we will have Cl-, because this is the correct oxidation number, and so we need 3 chlorides to compensate, let's say, the 3 positive charges of aluminium. And also with hydrogen, this is hydrobromic acid, so H is +1, so H+, and of course bromide will be -1. Okay, so this was very short, but just to refresh some concept. I think you already knew those things, but just to refresh them. Okay, so this one is already finished. Okay. Okay, sorry, any question on this very fast overview of oxidation numbers? No? Okay. Okay, so let's take a look in more depth at the biotransformation reactions that happen in the body. This topic is quite important because we will see in the following that toxicity of compounds can change in a very heavy way according to the biotransformations it undergoes in the body. So as soon as a toxicant, a poison, enters the body, it is subjected to several reactions. Okay, usually any compound in the body is modified as soon as it enters. As soon as it is absorbed. Okay, so mainly after, for example, if it enters the body into the intestine, it will be modified, of course, during digestion, but what we call biotransformation will happen after it passes the intestine wall and it is effectively absorbed, okay? Before it is digested, okay, but once it enters the body, it is effectively absorbed, biotransformation begins, okay? Usually, most compounds are modified in the body. Some compounds or some part of the total dose of a compound can be unchanged, can stay the same within the body and be finally eliminated or stored in some tissue exactly as it was absorbed. But this is not the most usual thing that happens. Usually we have a series of biochemical reactions, and in the body we can differentiate between two main kinds of reactions. The first kind is so-called toxicity mechanisms. Okay, so those are the biochemical reactions that cause the toxicity, okay? The mechanism through which the compound produces its toxic effect. And this, we can look at it as what the compound does to the body. On the other hand, the biochemical processes that biotransform the compound is what the body does to the compound. Okay, it's the vice versa in some way from the toxicity effect. However, those processes can change different compounds and also the same compound in different ways. They can activate inactive compounds. So we can have non-toxic compounds that are absorbed and the biotransformation changes them, making them toxic, okay? And usually those compounds are called protoxicant. This means that they are not toxic when they are absorbed, but when they are absorbed, the biotransformation, the so-called metabolism of the body, modifies them into some toxicant. So the first molecule, the original molecule, is the protoxicant, and then it is the body that transforms it into a toxicant. Or the body can modify the molecules, and these modifications can increase or decrease the molecule toxicity, okay? And in this case, we can say that the molecule is detoxified if, of course, toxicity is decreased, or it is toxified if toxicity increases. Okay. Regarding the specific part of biotransformation, we have two big parts, two big phases in biotransformation reactions. They are called phase 1 and phase 2 reactions. They are called this way because usually the first reactions that happen to the compounds in the body are those of the phase 1, of course, and then the compounds already modified by phase 1 metabolism undergoes also phase 2 reactions, but this is not always the case, okay? Some compounds can undergo directly phase 2 reactions without undergoing phase 1 reactions, okay? But usually it is phase 1 and then phase 2. Phase 1 reactions are modifications that introduce functional groups onto the molecules. We have seen before that biotransformation quite often makes molecules more hydrophilic. So phase 1 reaction introduce functional groups that usually are polar, okay, are hydrophilic. In this way, if I add a polar, an hydrophilic group to an existing molecule, of course, the molecule will become more hydrophilic. So the product of phase 1 reactions are usually more water-soluble molecule. And or these groups that we attach to the molecule can be something like a reactive groups that the body can use as an handle to carry out phase 2 reactions. In some cases, the original molecule, the original toxicant, is not suitable for phase 2 reactions. It's not reactive to phase 2 reactions. So the body carries out phase 1 reactions, changes the molecules in order for them to be suitable or suitably reactive to phase 2 reactions. Phase 2 reactions are called conjugation reactions because we have the binding of an entire substrate, an entire molecule, okay? In phase 1, we have just usually small polar functional group attached to a molecule, or we break down the original molecule to expose some functional groups. In this case, we bind a new molecule to the original toxicant. And usually, again, those molecules we conjugate with the toxicant are hydrophilic molecules, and they will be, so the resulting compound will be more hydrophilic, more easily excreted, and it is also usually less toxic. We have a lot of different phase 1 reactions and a smaller number, but still many phase 2 reactions. Of course, not all xenobiotics, not all toxicant will undergo all phase 1 reaction and then all phase 2 reactions, because enzymes, as you may remember, are specific for some substrates. So, since all these reactions, of course, need enzymes to be carried out in the body, we will see that just some enzymes are specific for the specific compound, the specific toxicant, and so just some reactions catalyzed by that enzyme will happen to that specific toxicant or poison and so on. Okay, so let's take a look at the most important phase 1 reactions. One of the most important, probably the most important class of phase 1 reactions is oxidation reactions. Oxidation can happen at most atoms of the molecule, so at the carbon, nitrogen, sulfur, or phosphorus atoms. And we can divide oxidation reaction into subclasses. Mono-oxidations are the oxidation reactions where oxygen, let's say real oxygen molecule as such is used as the oxidizing agent. Of the two oxygen atoms in the oxygen molecule, one is used to oxidize the molecule, and the other one is incorporated into water. So this is the reason it's called monooxidation, because just one of the two oxygen atoms is used to oxidize the substrate, while the other is incorporated into water. Those reactions are very important for xenobiotics, for compounds introduced into the body from the environment. And those enzymes are, let's say, the most important part of the enzymes that catalyze monooxidations are the cytochromes P450. They are abbreviated CYP. They are enzymes that contain an iron atom, so are iron-dependent enzymes. And most of them, almost all of them, are found in the liver. So you may remember that the liver is the biotransformation central in our body, and the most important enzymes of biotransformation are, of course, there, including CYP enzymes, cytochromes. Okay. Another important reaction is epoxidation. You may remember that this structure, this triangular structure with the two carbons both connected to the same oxygen atom, is called an epoxide. So it is produced by the oxidation of double bond, also double bonds included in aromatic structures, just like this. Here you can see that circle. The meaning of this circle is that we have the localized double bonds, but they are still considered reactive, more or less like double bonds. Okay, so the circle is very similar regarding reactivity to three double bonds, three alternating double bonds or conjugated double bonds. So here you can imagine a double bond, and under the action of oxygen, again, this is a kind of monooxidation. Here you can find the general kind of monooxidation. Here, epoxidation can be considered a subgroup of monooxidation, since oxygen is again, the oxygen molecule again is used as such to carry out the reaction, and just one of the two oxygens is attached to the molecule. But this is different because also epoxidation produces very reactive epoxide. You may remember from before that epoxide are very, very reactive compounds that readily undergo ring opening. This three-atom ring will open, producing a diol or a molecule with two alcoholic group, a diol. Again, this kind of reaction is catalyzed by cytochrome P450. This reaction produces a very reactive compound, and as we have seen before, very reactive compounds are very dangerous. They are quite often, let's say almost always, dangerous poisons. And this is also the case with the epoxide produced by epoxidation. So every time we find that the cytochrome system produces epoxides, we usually find also that this is a bioactivation. So a compound that by itself is not particularly toxic, is activated by the biotransformation reaction into a very reactive compound that is in turn very toxic. You will see in the following that polycyclic aromatic hydrocarbons, just like this one, are toxic compounds, not on themselves, but after bioactivation through biotransformation. And in fact, you can imagine that all of these aromatic nuclei contain a lot of double bonds, just like this one. Okay, so they can undergo multiple, just like this, first here and then here. They can undergo several consecutive epoxidation reactions, and every one of those reactions produces a reactive compound that can be toxic. Okay, so of course they can become quite toxic through biotransformation, through bioactivation. Those reactions, epoxidation and monooxidations, are oxidation happening mainly at the some carbon atoms in the molecule, but we can also have oxidation of non-carbon atoms of the molecule. For example, here we have this molecule. It's quite complicated, but it is not important to remember, of course, the specific formula. It is called 2-acetylaminofluorine, and this is just like the previous one, the previous polycyclic hydrocarbon, is not toxic in itself, but through oxidation at nitrogen atom, it becomes a derivative that is cancerogenic, okay, carcinogen. So again, we can see here an example of bioactivation. And again, for N-oxidation, the most important enzymes are cytochromes P450. Another important change that the molecule can undergo is alcohol dehydrogenation. Of course, the corresponding enzyme is alcohol dehydrogenase. The name says all, of course. This molecule is an alcohol. It contains the OH group, and alcohols can quite easily be oxidized to aldehydes if they are at the end of the molecule. This is a primary alcohol, so it becomes an aldehyde. If it was a secondary alcohol, it would become a ketone, but the mechanism is very similar. Also, aldehydes are relatively unstable groups that can easily be further oxidized to carboxylic acids, COOH. Of course, aldehydes are the carbonyl group at the end of the molecule, and when they are at the end of the molecule, they can be further oxidized to COOH, to carboxylic groups. Ketones, they are in the middle of the molecule, so they cannot be further oxidized. They cannot form carboxylic. Sorry, just a moment. Okay. They cannot be oxidized to carboxylic groups without breaking down the molecule. This kind of reactions, alcohol dehydrogenation, is quite important as a detoxification process, since aldehydes are quite sorry, not the first step, but the whole reaction chain. So going from alcohol to aldehyde and then to carboxylic acids is an important detoxification mechanism. This is because aldehyde are more lipophilic than alcohols in general, and also more toxic than alcohols. So the first step increases a bit toxicity, but then if the molecule becomes an acid, COOH instead of COH, the molecule becomes very, very hydrophilic and very easily modified through phase 2 reactions, and so further detoxified. But we also have a lot of different reduction reactions. Okay, until now we have seen mostly oxidation reactions. Of course, molecules can also undergo reductions. For example, here you can see aldehyde reduction. This is, of course, exactly the reverse or the inverse of this reaction. You can see that this is an equilibrium. So if we start from a big dose, let's say, of alcohol, of course, the reaction will go toward the aldehyde. But if we start from a big dose of aldehyde, the opposite mechanism can happen and we can have aldehyde reduction. And in this case, usually, we have a lower toxicity from the alcohol and also a more hydrophilic molecule than the original aldehyde. And in the same way, ketones are more lipophilic and more toxic than the corresponding reduced alcohol. And another important form of reduction is the reduction of alkenes. You may remember we have very briefly talked about it in one of the first lessons. So the double bond, carbon-carbon double bond, can open and the carbons can be hydrogenated. So this is also often called hydrogenation of double bonds. And this is, of course, a reduction because we know that hydrogen has a very low electronegativity. So when a carbon-carbon bond becomes a carbon-hydrogen bond, carbon will decrease its oxidation number, so it will become more reduced than before. Generally, the enzymes that carry out reduction reactions are called reductases. And again, most of them are found in the liver. But we know that also many compounds in general, but of course we are particularly interested in poisons, can be reduced by bacteria in the intestine. So this is another important thing that can happen before the compounds are absorbed. The fact that some modifications can happen through the gut flora in the intestine, and also, of course, the modified compound can be absorbed and then go into the body and do what it does. A very, very important phase 1 reaction is the hydrolysis reaction. You may remember we have seen it briefly when we talked about catabolism reactions for proteins and lipids and polysaccharides. Hydrolysis is a reaction involving water where the molecules are broken down. In this case, we have an ester, and we know that esters can be hydrolyzed to an acid, carboxylic acid, COH, and an alcohol. but many kinds of hydrolysis reactions, for example, amides can be broken down into, again, an acid and an amine, and so on and so forth. The enzymes carrying out hydrolysis are called hydrolases. Also, another reaction involving the molecule breaking down in some way is dealkylation. In this case, we should have an heteroatom here, nitrogen, oxygen, or sulfur mostly. And so we can have that the alkylic group, the alkyl group here, in this case it's always methyl, but it can be anything really. Okay, any alkyl group can be detached from the molecule, leaving the heteroatom alone, let's say. So from this secondary or tertiary amine, by dealkylation, we can produce the primary or secondary amine according to the starting one. Or if we have an ether, for example, we can free the corresponding alcohol, and from this thioether we can produce the thiol. And in all cases, the other part of the molecule, so the alkyl part, is transformed into the corresponding aldehyde. So we are producing, let's say, a smaller molecule broken down and an aldehyde. Or in some cases, the ketone. But the important thing in this case is that it's not the simple alkyl group that goes off, but it is an oxidized form of this alkyl group, usually aldehyde or ketone. This is another kind of dealkylation reaction. For example, this is a sequence of different reactions. First, oxidation, mono-oxidation here at the carbon to produce the alcohol, and then dealkylation here between the carbon and the nitrogen to produce this oxime, and then reduction of the resulting compounds to form a diazo group. But this is not important. What is important is that we can have a sequence of reactions with different phase one reaction happening on the same or on different parts of the molecule. So the final, let's say, molecule can be also quite different from the starting one. Also, when we have organohalogen compounds, the most frequent reaction is dehalogenation. So the molecule simply loses the halogen atom, which is replaced by one hydrogen. In this case, we have a reduction, okay? So it's called reductive dehalogenation. Again, when we replace some atom with hydrogen, usually it is a reduction, okay? Or we can have oxidative dehalogenation, and in this case, the chlorine, the halogen atom, is replaced by an oxygen atom, and also it can be further oxidized. The first step is the formation of an alcohol, OH here, and then further oxidation to carboxylic acid atom. Sorry, carboxylic group, not atom. Okay. Okay. Let's see. Okay, so we have finished the phase one reactions. In Is something unclear? There are other questions? No one? Okay, so I see that it's already 10 past 10, so let's stop here for now. Brief break, and in 10 minutes I will be back. Okay? See you later.
Okay, bye, thank you.
You're welcome. And please write if you have any question, okay?
Sure.
Okay. I am back. Okay. So you hear me, I hope, and you also see the slides. I don't see any questions in the chat, so I think we can go on. So we have seen phase 1 reactions. As you have seen, it's a lot of different reactions that can happen, but mainly we have oxidation, hydrolysis, dealkylation, and reductions. These are the classes. Of course, within oxidation, we have a lot of subclasses. Within reduction, we have a lot of different reactions, but these are the, and also halogen removal, okay, of course. These are the most important classes. Then we have phase 2 reactions. As we have said, conjugation reactions are carried out by attaching, by conjugation of a full molecule, more or less a full molecule, to the starting molecule, or to the molecule that has already undergone phase 1 reactions. We have seen before that phase 1 reactions can produce an epoxide, can free an amino group, or produce carboxylic, alcoholic groups. So any of these groups is reactive to conjugation reactions. And conjugation reactions are mainly reactions that produce more polar, more hydrophilic compounds. And so also less toxic compounds. You may imagine that if the toxicity of a poison is due to its specific structure and also to the shape of the molecule, attaching an entire molecule to it can change its characteristic quite strongly, okay? And so probably also the toxicity will be lower. Probably the single most important phase 2 reaction is conjugation with glucuronide. Glucuronides are this kind of compound here in the lower right part of the molecule. If you remember the glucose molecule from polysaccharides and sugars, this is just like a glucose molecule, except the last carbon in the chain is oxidized to carboxylic acid instead of an alcoholic group. Okay, so in fact it is called glucuronide. So the gluc part means the molecule comes from glucose. The name of the enzymes carrying out this kind of reaction is UDP, glucuronosyl transferase. So it's quite strange. Of course, transferase means that the enzyme transfers some molecule to the to another molecule. Glucuronosyl means that it contains the glucuronyl, this part of the molecule, which is a reactive form of glucuronic acid. So this is the active form of glucuronic acid, which is glucuronic acid bound to an UDP molecule. UDP means uridine diphosphoglucuronic acid, or something like this. But uridine is this. And you may remember from ATP, for example, adenosine triphosphate. This is uridine diphosphate connected to, linked to a glucuronic acid molecule. The basic structure is the same, except here we have an uracil instead of adenine. But the structure of the molecule is exactly the same as ATP, or better in this case, ADP, because we have two phosphate groups. And then instead of the third group of ATP, we have the glucuronic acid molecule. But the similarity between the two molecules is not an accident, okay? Because we know that the third phosphate in ATP is the energetic one, the one where when the link is broken, we release energy. And this is exactly the same. This is an activate form of glucuronic acid, exactly because this bond is highly energetic due to the presence of UDP. And in this way, the molecule is ready, the glucuronic acid molecule is ready to react because breaking down this bond releases a lot of energy, and so this energy can be used to form a new bond with the target molecule, with the toxicant we are considering in this moment. Okay, so those are all examples of glucuronidation. They are quite small, the images, but you may imagine that this is an oxygen, is an alcoholic group, and it is changed to a glucuronide, and this is called, of course, O-glucuronide. It means that the glucuronidation happens on an oxygen atom or on a nitrogen atom here, you can see, or on a sulfur atom, or also on a carbon atom. So glucuronidation can happen on mostly any atom in the molecule, but the most important ones are surely O-glucuronidation, so on the oxygen molecules of compounds. And you may imagine that this is very, very, very hydrophilic molecule. Glucose is extremely soluble in water, and glucuronic acid, it has a carboxylic group here instead of an alcoholic group, is equally or even probably a bit more soluble in water than glucose. So you may imagine that attaching this extremely hydrophilic compound to any molecule will make it really different from the starting molecule, so probably less toxic in itself, and also very, very more hydrophilic than the starting molecule. Glucuronidation is the most frequent phase 2 reactions. Okay, we know a very, very wide variety of glucuronides produced by biotransformation. Less frequent, but very important, is glutathione conjugation. glutathione is probably the single most important detoxifying compound in our body. Glutathione is this molecule. It is a tripeptide. It means that it is made up of 3 amino acids connected together. It is exactly glutamine, cysteine, and glycine. Of course, connected through peptidic bonds with a small modification, because usually this bond should be between this nitrogen and this carboxylic group, okay? Because this is the peptidic carboxylic group. Since, however, glutamic acid is as another carboxylic group at the end of the side chain, in this case, it is linked here, but it's not important for our purposes. The important thing is that glutathione is very easily attached to a lot of different molecules, and it is, of course, relatively hydrophilic, because this part of the molecule contains an amino group, which is hydrophilic, a carboxylic group, hydrophilic, and another carboxylic group here, again, hydrophilic. It is the thiol group here that generally reacts with molecule. Here we can see that glu, cis, gli, it means glutamic acid, cysteine, and glycine. And here we have the thiol group of cysteine, and it reacts with the reactive group, whatever it is, of the xenobiotic to produce this kind of molecule, glutathione conjugate. And after the conjugate formation, we usually have the loss of glutamic acid and of glycine to produce a simple cysteine conjugate, which is in turn quite hydrophilic, because we only have the amino acid part of the glutathione molecule, so an acid and an amine, both hydrophilic. Both the glutathione and the glycine conjugates are directly excreted, often in bile. You may remember that this is an elimination, a secondary elimination pathway, but it can become quite important in the case of glutathione. And then this cysteine conjugate can undergo another phase 2 reaction, which is the acetylation reaction. So the addition of CH3CO group, this is the acetyl group, okay? So an acetyl group can become attached to the amine of cysteine to produce mercapturic acid conjugate. This part of the molecule is a mercapturic acid here. But this is not really, again, the specific structure is not important. What is important is that those are much more hydrophilic than the starting molecule, and they can be eliminated quite easily. In this case, acetylation makes the molecule a bit more lipophilic. So this can be detoxifying steps. This step is not always detoxifying, can also increase compound retention in the body. But those two first reactions are very, very frequent and very important. Conjugation with glutathione is very important in detoxifying compounds. Quite frequent conjugation with sulfate happens in the body. As you can see here, mainly alcohols or phenols and amines can be conjugated to sulfate. Sulfate is a good conjugation group because it is permanently charged here, okay? You may remember that sulfuric acid is strong, is in fact a very strong acid. And so the sulfate group is very strong. This means that this oxygen is always charged. It has always a negative charge. So as you may imagine, this permanently charged group is very hydrophilic. Okay, so the molecule becomes a bit larger, not as much as with glucuronic acid, but a bit larger and a lot more hydrophilic. Okay, again, as usual, we have enzymes carrying out this kind of reaction. They are called sulfotransferase. Another important reaction is methylation. Methylation happens with the transfer of a methyl group on the target molecule. Again, as we have seen for glucuronic acid, here we have a methyl group which is attached to a high energy bond here. And again, you can see this structure, which is very frequent with high energy compounds in the body, okay, is a recurring leitmotif. In this case, the full molecule is known as S-adenosyl methionine. This is methionine, which is an amino acid, here, acid and amine group. This is methionine with a methyl on the sulfur atom, so this is the methyl group transferred, and again on the sulfur we have an adenosine, so S-adenosyl methionine. This methyl group can be transferred to oxygen, nitrogen, or sulfur atoms. Why? Because here you can see a plus sign, but really when the molecule reacts with other substances, it is as if this plus charge is here on the methyl group, and carbon really hates to be positively charged, also negatively, but it is even more difficult. But positively charging carbon atoms is quite difficult, and it makes them very, very unstable. So this compound acts as if we had a very, very unstable methyl ion, methyl cation, in fact. So this ion has a positive charge, and carbon wants very, very strongly to lose that positive charge, of course, taking electrons from atoms that are rich in electrons. And you may remember that oxygen, nitrogen, and sulfur have electron pairs, let's say unbound free electron pairs around the atom. Oxygen has 2 electron pairs, nitrogen has 1, sulfur again has 2. So those electron pairs are very, very attractive. Of course, they are negative because they are electrons, and they are attractive to the positive charge, positively charged methyl group. And so it easily reacts with those atoms in other molecules. This is an exception to the general rule that biotransformation makes compounds more hydrophilic, because of course methyl and in general alkyl groups are lipophilic. So when we attach a methyl group to any compound, we will make it more lipophilic, and so it makes it more difficult to eliminate from the body. Okay, I guess this is all regarding biotransformation. Is everything clear? Sorry. Is everything clear? Yeah? Okay. If everything is clear, we can go on with the first part of a specific toxicology part, where we will take a look at different classes of compounds, starting, of course, from the simplest compounds, which are the elements. Okay, 3 elements, mainly metals, in this part of the periodic table, can be easily found in nature and also as a product of human activities, and they can have even very strong toxicity. So, okay, thank you for confirming everything is clear enough, at least enough. So we can start talking about lithium. Lithium is here. So is the first group. It is an alkaline metal, and it produces cation with just 1 positive charge. Cation, lithium cation, is used quite frequently as a drug to treat a disease called bipolar disorder. In particular, lithium carbonate is used. Is the most effective agent against bipolar disorder. I don't know if you know this. This disorder is an alternance between depression and exaltation, moments of deep depression and moments of so-called manic behavior, where the person is exactly the opposite of a depressed person. Okay, so it is exalted. It feel they feel exalted. They feel omnipotent and invulnerable, and so on and so forth. And both states are quite dangerous, because when one is depressed, it can tend to suicide or try to suicide. And when one is exalted or manic, it can do very dangerous, very stupid actions. And so this kind of disorder is quite dangerous. Lithium is also used in many industrial applications. All batteries in our cell phones, and nowadays really in most portable electric instruments or apparati, are powered by lithium batteries. So lithium and lithium ion is very, very widespread nowadays in our homes, also in our environment, because unfortunately many batteries get discarded into the environment, and so it is quite easy to come in some way in contact with lithium. Lithium is mostly toxic toward the kidneys, and if kidney toxicity happens, we have that blood is not properly filtered, is not properly detoxified. Substances that should be eliminated are not, in fact, eliminated by the kidneys. Okay, and so this makes high levels of albumin and glucose appear in the urine. This is a bit like the opposite of what I say, because this is the excretion of things that shouldn't go in the urine. So kidney damage can impair elimination of toxic compounds, but it can increase elimination of essential compounds. Okay, I mean, albumin should stay in the blood, glucose should stay in the blood. Okay, if we have albumin or glucose in the urine, this means that we have something bad happening in our body, and in particular probably in the kidneys. Okay, in this case, of course, lithium is toxic to kidneys. So this is one of the form of damage, important damage. We can have symptoms in the central nervous system, because lithium is very similar to sodium, and sodium is involved in neural transmission. Okay, so we can have impairments in how our nerves, our nervous system works, and so tremor, paralysis, equilibrium impairment, and so on. And also sodium is involved in all kinds of not only of neural transmission, but also of muscle contraction. So again, excess of lithium can cause changes, modification in muscle contraction. And of course, the most dangerous form is changes in heart contraction, so arrhythmias, and also if hypertension and heart failure can happen. I mentioned only similarity to sodium, but it is also similar to potassium, as it is written here, because they are from the same column, from the same group, okay, sodium and potassium. So they have similar properties, okay? And so lithium can go, let's say, can go where sodium or potassium should be. And it has similar but not the same properties. And so its presence can modify both neural transmission and muscle transmission, and thus muscle contraction. Okay, the next class of toxic elements are heavy metals. Heavy metals, of course, is a group of elements, it's not a single element, are a group of metals that have relatively high density. This is why they are called heavy metals. The most important ones are chromium, mercury, lead, cadmium, and arsenic. In fact, arsenic is not a metal. Is a metalloid, because arsenic is here, but it has mostly the same toxicity as real heavy metal. So it is included in the class, even if it is not really a true metal. Okay, here we have lead, cadmium, mercury. So you can see that those are metals in the lowest rows of the table. So they are among the most heavy ones, okay? Why those metals and not other metals with similar weight, with similar density, are the most important, the most dangerous? Because they are very frequently used in industries, in the manufacturing of some products. They are very toxic, and they can be distributed all over the body once they are absorbed. Moreover, when heavy metals enter the environment, for example, as discarded materials from households or from the manufacturing industries, they go into soils and sediments, and they can stay there for very, very long times. So heavy metal contamination is a long-term contamination, because heavy metals are not used by living organisms, by bacteria and so on. They are not transformed into something else, or sometimes they are even transformed into even more toxic compounds. So the contamination of soil and sediments with heavy metals is a very, very dangerous environmental problem. Mercury is toxic as an element itself, so a metal, okay? You may remember that mercury is a liquid metal, and it is toxic in its metal form, its liquid metal form. All other metals, all other four most important heavy metals, are dangerous not in their metal form, but in their salt form. They, of course, are metals, so they form cations. Why are they more dangerous as cations? Because they are more soluble, okay? So they can be more easily absorbed. Or when they are bound to alkyl groups, when they are bound to short chains of carbon atoms. This is called an organometallic form. It means that the metal is bound to an organic residue. So they are mostly toxic as cations or as organometallic compounds. Since they are in their mostly in their cationic form, they are very reactive towards those groups that have high electron density. Do you remember we have said it before that oxygen, nitrogen, and sulfur have a lot of electrons, of free electron pairs that are exposed, are available for reaction. So, of course, electrons are negatively charged, so they are quite exposed to reaction with cations that lack electrons, okay? And you may imagine that carboxylic groups, amino groups, and thiol groups are very important parts of amino acids and thus of proteins. So heavy metals have the potential to react with many proteins, and in particular with many enzymes, and this reaction deactivates the protein, in particular deactivates the enzyme. So you may imagine that if you disrupt enzyme activity, any kind of damage can happen to the cell according to the enzyme, to the specific enzyme that is inactivated. And in fact, the exact symptom of heavy metal poisoning depends on the specific organ that is attacked by the metal. Every heavy metal has a specific affinity for one or more organs. And so it is that organ that is damaged preferentially to other organs. Okay, so they can cause very wide kinds of damage, but usually they damage a specific organ. Okay, so the specific toxicity is not due to the specificity towards the single enzyme or the single compound target, but it is governed, it is ruled by specific affinity of the heavy metals toward an organ. Wherever it goes, it damages the specific organ. Chromium is one of the most toxic heavy metals. It can be found as chromium 3+ or chromium 6+, so trivalent or hexavalent chromium. It can exist as different oxidation numbers, but +3 and +6 are the two most stable forms. +3 chromium is an essential element for our body, for most animal bodies. So we need small amounts of trivalent chromium, in particular for glucose metabolism. Lack of chromium, of trivalent chromium, causes something like diabetes. But the +6 form is instead a really toxic element. So you can see that a simple oxidation from 3+ to 6+ means that the same metal goes from an essential element to a toxic one. In particular, the +6 form is, let's say, is usually found as chromate Cr04 2- or bichromate Cr2O7 2-. In this case, here we can see sodium chromate and sodium bichromate, but of course the important toxic part is chromate and bichromate. Chromates and bichromates are water soluble, and so they can be transported very easily within water, and they can also, if they are present in the air, and this happens quite frequently in city pollution. Chromium is a frequent pollution due to the burning of gasoline and similar combustibles. And it is also a strong carcinogen. So it can be easily absorbed through the lungs when it is in the air, and it is mainly a carcinogen. Okay, one of the few substances that are surely carcinogenic to humans. Most compounds usually considered carcinogens are not demonstrated to be surely carcinogenic, but in this case, chromium 6+ is surely carcinogenic. Okay, I see it's 11 o'clock, so I will stop here for the second hour, take the usual break, and if you have any question, I know I repeat myself a lot, but if you have a question, please write in the chat. Okay, see you later. Hi, welcome back. So, I see there's a question. In which detail we should know all the structures, mechanism? Okay, I don't want you to learn by heart any structure. You should learn to recognize, let's say, the most important groups, have an idea of how is the structure or what kind of functional group some class of toxicant contains. But you don't have to know by heart really no structure. Okay. I mean, I am showing you a lot of structure, of course, because this is environmental and toxicological chemistry course, and in order to understand the chemical reaction and the toxicity of compounds, we need to know, not to know, but to see and to understand the structure and how they work. They work. Okay, but you don't have to learn anything by heart. Maybe you will have to learn by heart some effects, okay, some toxic effects or some properties of maybe a class of poisons, but not structures, I think, at all, okay? But at the end of the course, in the last lesson, I will show you an example of the exam. You know that the exam is a series of 15 questions, okay? So I will show you an example of those 15 questions, so you can better understand the kind of knowledge you should have in order to pass the exam. Okay. Okay. I hope this is clear. So we have seen for now among elements lithium and chromium. Chromium is part of the class of heavy metals. And then we can take a look at mercury. Mercury, we already know that is the only liquid metal at room temperature. The most important mercury ions are the monocation and bication, so +1, +2 cations. Since it is liquid, mercury is not since, but mercury is liquid and it is also volatile, okay, in its metallic form. This means that when we are in the presence of metallic mercury, part of it will evaporate in the environment, and so we are exposed to its vapor, okay? And so, let's say, strangely for a metal, absorption through the lungs is quite important, it's quite strong, okay? Up to 80% of mercury vapor can be absorbed through the lungs, okay? On the other hand, apart from the metallic form, the cations are not volatile, of course, but they can be very easily absorbed through the skin and through the intestine. In particular, when they are in metallo-organic form. the metallic form of mercury is oxidized in erythrocytes, in the red blood cells, to the cation. And it is the cation that has the specific toxic mechanism we have detailed here. Okay, so here you can see that heavy metal toxicity involves the cations, and mercury is easily absorbed as a metal, which is not a cation, of course, but it can be easily oxidized to mercury in erythrocytes. However, it can also reach the brain, and this is, as you know, very, on the one hand, it is very difficult because of the blood-brain barrier, but it is also very dangerous. Mercury as a metal is uncharged. It is quite lipophilic, especially if it is not especially. It is quite easily absorbed, and it passes the blood-brain barrier because it is lipophilic. Okay. And then, if it is absorbed into the brain, it is oxidized in the brain and stay there because it cannot go out through the blood-brain barrier because it has become lipophilic, more lipophilic. Okay, so this is quite peculiar as a mechanism because we know that usually heavy metals are toxic in their cationic form, but mercury is toxic also in its metal form because it is easily absorbed, it easily passes into the brain, and then it is bioactivated. You remember bioactivation, by oxidation, and transformed into its cationic form, which is the true toxic element. Mercury is reacts mercury cation reacts mainly with thiol groups, so SH groups, and those groups are very, very frequent in many proteins, so it can disrupt a lot of different function in the body. In the central nervous system, we can have at first tremors, problems in thinking clearly, insomnia, depression. So as you can see, these are very aspecific symptoms. A lot of different, let's say, problems, even not true disorders can cause tremors or depressions and so on. So at first it's very difficult to diagnose mercury poisoning, and mercury is also toxic toward the kidneys, and so damage to the kidney means that they usually stop working, and a lot of compounds can pass from the blood to the kidney, to the urine, and in particular albumin is a sure sign of kidney damage. Of course, if kidneys stop working altogether, this is very dangerous, and you may need a transplant or dialysis for life. Among the cations, it is mercury 2+, which is more dangerous because it is more soluble than mercury 1+. But organomercuric compounds, organometallic compounds, are even more dangerous because they are more lipophilic, and so they can pass membranes, and they can concentrate along the food chain. What does this mean? This means that mercury, let's say that the most important form of mercury pollution is due to industrial wastes. And when industrial wastes go into water, of course, they pollute the microorganisms there that can intake a lot of mercury. And then when some seashell, its microorganism, it's let's say those microorganism like not monocellular microorganism, but microanimals like krill and so on. Each small organism will have a small amount of mercury within it, and the larger organism, the larger seashell or crustacean or fish that eats them, it's a lot of them, so it will intake a lot of mercury. And then a bigger fish will eat a lot of smaller fish. Each one of them, each one of the small fish will have a lot of mercury. So the larger fish will intake even more mercury than each of the small fishes, and so on and so forth. So this is the meaning of concentration along the food chain. Okay, this means that each predator concentrates the toxicant more than the prey it feeds upon. Okay, this happens exactly because mercury is very lipophilic, and in particular organomercuric compounds are extremely lipophilic. So this means that once they become absorbed, they will be stored into fat tissue. And once there, they will not go away. Okay, once you are, let's say, contaminated with mercury, mercury will go, of course, all around the body. It can cause damage, but the bulk of mercury will go into the fat tissue, and it will never go out. Simply stay there. So every time we have a successive exposure to mercury, we will have an increase in the accumulation of mercury in the fat tissue. And so this is the reason why we have slow chronic poisoning due to mercury, because it accumulates, and when the concentration reaches a high level, we will have the symptoms. And it is the same reason why mercury and the other heavy metals concentrate along the food chain. Because once contaminated, you never excrete, you never eliminate mercury, unless you undergo, of course, a specific therapy, okay, with specific drugs. But of course, for animals, microorganism in the water, it is not possible. And in fact, the most important, well-known incident of mercury poisoning happened in Minamata Bay in Japan, when mercury from a chemical plant near to this bay contaminated the water, and so seafood. And of course, along the food chain, the fishes, in particular tuna is very large fishes, and through tuna also people, of course. When something concentrates along the food chain, usually the main victims are humans, because humans are at the top of the food chain in many cases. Okay, and so more than 100 people were poisoned with mercury, and about 50 of them died, and also cases of congenital defects were observed. So this is, and let's say, a demonstration that probably mercury is also toxic toward the DNA. It can cause mutation, is a mutagen, and teratogen. Teratogen means that it can cause defects in unborn babies. And so, of course, when they are, if they don't die during pregnancy, they are born with physical or mental defects. Okay, this is the meaning of teratogen. So probably, most probably, mercury is not only toxic but also carcinogenic and mutagenic, and thus teratogenic. Why is mercury present in the environment? Through manufacturing. Elemental mercury can be found, or could be found in the past, in thermometers and barometers. Now in thermometers has been banned, and it's only present in very, very specialized kind of thermometers that is not very important. It used to be present in fluorescent light bulbs, in particular in so-called neon light bulbs, or let's say in Italy we call them low consumption light bulbs. Okay. Fortunately, it is almost totally absent from LED light bulbs. So in the last years, it is starting to disappear from this kind of use. And it was also used in dental amalgams. An amalgam is a mixture of mercury and another metal that can form something like a paste, something like a metallic glue that was used to close holes in teeth. And then mercury evaporates, and it leaves a stopper, a metallic stopper in the teeth. Nowadays, those kind of operations are done with ceramic polymers or other kinds of polymers, and so even in this field, mercury is less and less used. However, those are uses of mercury where mercury is useful. Okay. However, mercury can be present in the environment also due to contamination, since it is very, very frequently present in coal, in oil, in gasoline, and so when they are burned, mercury will evaporate into the air. And in a similar way, waste, household and industrial waste, which is incinerated, can contain mercury, which upon incineration will go in the air. Okay. Okay, another heavy metal, quite well known for its toxicity, is lead. And contrary to mercury, it is very, very frequent in industrial manufacturing. It's the fifth most used, most produced metal in industrial manufacturing. Lead compounds are mostly ionic, differently from mercury, where we have a lot of covalent compounds. And this is true for 2+, lead 2+, but we also have, not so frequently, but it is present, lead 4+, and it forms this compound, lead dioxide, and here the bond is covalent. Lead dioxide is a very strong oxidizing agent. So, as you may imagine, it's also quite toxic, because we know that strong oxidizing and reducing agents are toxic. In reality, lead is present as a contaminant almost everywhere. If we analyze almost anything, we will find very small amounts of lead. So lead pollution can happen very frequently in almost any environment. It is relatively, of course, the smaller the amount of lead, the longer it takes to develop toxicity. But it is mostly frequent in the air, so in the atmosphere, and absorption happens as a consequence through the lungs. Lead is quite similar to calcium, and we know that the most important use of calcium in our bodies is in the bone. So once absorbed, lead goes to the bone, since it is similar to calcium, so it is incorporated into the bone as if it was calcium, and it can stay there up to 20 years. Even if bones are renewed, are destroyed and rebuilt, of course, just small parts of the bone are destroyed and rebuilt continually. Once lead goes into the bone, it can stay there for about 20 years. And since lead is not exactly identical to calcium, it's only similar, it can cause, of course, problem in bones. It can make them more brittle, more easily breakable. But we know also that in the bone, the production of blood cells happen, okay? And so lead can also inhibit the production of blood cells, and in particular of red blood cells. To build red blood cells, bone needs hemoglobin. Hemoglobin is the protein that transports oxygen in blood. And so if we stop production of hemoglobin due to the toxic effect of lead, we stop producing red blood cells, and so we have a disease called anemia, and of course other kinds also of anomalies in the blood composition. Also, lead can affect the central nervous system and produce neuron degeneration, edema. It means swelling of the tissues, and cell death, neuronal death. You may imagine that if the cells in our blood, in our brain, and in particular in the cortex of the brain is where our higher thinking happens. So if those cells die, this is, of course, really, really dangerous. It can lead, for example, to dementia. Okay, it can also interfere with also other kinds of neural transmission, but this is something, let's say, included in the previous toxicity, and also some toxicity toward the kidney with the same mechanism as mercury we've seen before. Some of these effects can be reversed through decontamination, but some of them are not. In case of poisoning, we can administer so-called chelation therapy. Chelation means that we administer some compound like this. You can, of course, you don't have to remember this kind of structure, but this compound is called EDTA. And you can see here the asterisks mark carboxylic, 4 carboxylic, and 2 amino groups. And you may remember that all heavy metals are very attracted by those kinds of groups, exactly carboxylic and amino groups. So their mechanism of toxicity is by binding to carboxylic, amino, and thiol groups. So if we administer some substance like this that contains a large number of carboxylic and amino group and of thiols, of course, this means that they will react very easily with lead and with other heavy metals. And since this kind of compound is quite hydrophilic, it has a lot of carboxylic groups, it has a lot of at least partial charges, because of course carboxylic groups are acidic, so they can take a charge. And so the reaction between EDTA and lead produces a new compound. It is called a complex that is quite hydrophilic and can be easily eliminated. So the most important, let's say, toxicity parameter of heavy metal, which is their lipophilicity and their tendency to stay in the body, is reversed by treatment with EDTA or with BAL. This is 2 molecules of BAL. This is one, this is the other one. And in the middle, you can see lead. In this case, BAL has 2 thiol groups that can react with lead to produce another kind of complex. Chelation means formation of complexes, and this complex is quite hydrophilic and can be easily eliminated. Again, we have alcoholic groups that are very hydrophilic. So this is the main form of therapy in case of heavy metal poisoning. It is called chelation therapy. Okay, is it clear? I hope. How does this kind of therapy work? Okay. One of the main uses of metal lead was the use in car batteries, and also, unfortunately, in ammunition, in shots for pistols and revolvers and rifles and so on. This use, unfortunately, as we have seen even yesterday, is very, very frequent still. For car batteries is still very widely used, although, for example, electric cars have lithium batteries, not lead batteries anymore, but normal, let's say normal gasoline or diesel cars have still lead batteries. It was used also in plumbing for homes and industrial buildings, but nowadays it's very, very infrequent. But it can be found in old homes and so on, and it can release small amounts of lead into the water. So this can be a source of chronic poisoning. It was also used extensively in paints because many lead compounds are very colored, strongly colored in yellow or a very, very strong white. So they were very frequently used. In this case, you can see that we have both lead and chromium in the same compound. So twice the dose of heavy metal in just one compound. This is was very, very dangerous in a chronic poisoning. But it has been prohibited in all paints after 1978. But again, old homes, old buildings can still have some paint containing lead, and many times it can have been painted upon with other kinds of paints, but under the external layers of paint, of new paint, you can find lead paint. So maybe during renovations or other kinds of or demolition works, lead can be released from old layers of paint. It was used also for soldering, but again, we have nowadays different kinds of soldering materials, so it's not so frequent. Historically, of course, lead was used extensively for plumbing by Romans, some historians think that it could be a reason why the Roman Empire has fallen, because lead in plumbing led to chronic poisoning, and so to dementia and to widespread symptoms and diseases, and so this led to decadence in the Roman Empire. This is just an hypothesis. It's not so sure. Okay, but it's interesting hypothesis. Lead was added to gasoline in the past because it was very important to avoid gasoline exploding in the engine during its work, but it has been eliminated since a lot of years, I think about 30 years or so, in the USA and Europe, but it is still used in gasoline in some poorer countries. Okay, so in some countries still lead can be present in the air due to vehicle emissions. And also, of course, from landfills, from discarded batteries and this kind of products, if we don't dispose of them properly, lead containing materials have to be disposed in a special way, and they are to be differentiated in the waste management. but if there are not, they lead can leach from landfills into the soil, and so it can contaminate the location of the landfill, or if it reaches water, it can also be transported elsewhere, and so on and so forth. Okay, arsenic, we have seen that it is not a metal, it is a metalloid, but it has the same kind of toxicity as heavy metals. The two most frequent arsenic ions are arsenic 3+ and arsenic 5+. Arsenic is quite common as a contaminant in shellfish, of course through the water. Again, here the main problem is waste from manufacturing, in particular oil manufacturing, oil distillation is a very big producer of arsenic. Arsenic can be absorbed both from the air through the lungs and from food in the gastrointestinal system. Arsenic can undergo a lot of different reactions, and a lot of different compounds with different properties are known. So it is quite difficult to have a complexive overview of this element, but the most important ones are +3 and +6 cations. So arsenic is in the same period as phosphorus. Sorry, okay, here you can see nitrogen, phosphorus, arsenic. So again, it has similar properties to phosphorus, and so it can be incorporated instead of phosphorus in some metabolic pathways. Here you can see this is a piece, let's say, of the citric acid cycle. You remember where we obtained energy from sugars, okay? And here we have NAD+ that becomes NADH. And here we have ADP that becomes ATP. And this is one of the steps where we produce ATP during cellular respiration.